Good afternoon, everyone. Please have a seat. Find a space. Thank you. Good afternoon. Welcome to the Nye Lecture 2012, sponsored by the AGU Cryosphere Focus Group. My name is Ann Nolan, and I am the outgoing chair of this focus group. Yes. Before our Nye Lecture, we're going to recognize the 2012 recipient of the Cryosphere Young Investigator Award, Dr. Ian Eisenman, which will now be presented by his PhD advisor, Dr. Ellie Zipferman.
Thank you. So I'm here standing for John Wetlaufer, who nominated Ian, but I'm obviously delighted to do this. So let me just read what John wrote for Ian. One can appreciate the dramatic role of sea ice as a climate player when noting that during a single season, the areal change of Arctic sea ice cover is 4 times larger than the area of the ice-covered Greenland. This seasonal cycle and its observed recent trends is just one of the many aspects of sea ice and climate that are of interest to Ian Eisenman. One can study the role of sea ice using 3 different approaches, using climate general circulation models, interpreting satellite data, or developing low-order theoretical descriptions. All of these approaches are necessary to develop an understanding and prediction capability, and Ian has embraced all of these approaches. Already during his PhD, he began to develop a dual approach of using theory and comprehensive climate models. While participating in the 2006 summer program in GFD at Woods Hole, the interaction with the late Norbert Untersteiner motivated him to construct an observationally consistent low-order thermodynamic sea ice model. Ian excels at distilling the complex processes governing sea ice into simple theoretical models. He then studies these models carefully and enriches our intuition of how sea ice cover varies naturally and may respond to climate changes. Understanding also that our main observations of sea ice come from satellites, Ian delved into their analysis while a postdoc at both Caltech and the University of Washington at the same time. This year, this is where John really excelled in writing this. This year, he joined the faculty at Scripps, where he continues to think about ice while gazing out at the sunny, warm California beach. Well done, I think so. It is a pleasure that Ian Eisenman's creativity and skills are being recognized by the AGU Cryosphere Young Investigator Award. We all look forward to seeing what set of issues in the cryosphere he will address next. Congratulations, Ian.
Thank you so much, Ellie and John. It's a great honor to be receiving this award from the Cryosphere Focus Group. Very briefly, I want to thank a few of my terrific mentors who have helped to shape my approach to scientific research and guided my career trajectory. Ellie Zipperman, John Wetlaufer, Tapio Schneider, David Battisti, Cecilia Bitz, and the late Norbert Untersteiner. And I'm also grateful to many members of the cryospheric sciences community for their encouragement and support of my research, including Ron Kwok, John Walsh, Ron Lindsay, Don Perovic, Alan Thorndike, Steve Vavris, Walt Meyer, Helen Fricker, Mike Winton, Eddie Carmack, Ken Golden, and many others. It's truly a privilege to work and interact with this community. Thank you.
We have an amazing young community in our focus group. It's just great. In this keynote session, we recognize the outstanding glaciological accomplishments of Dr. Liz Morris, with the Nye Lecture. This keynote lecture is named after John Nye, a pioneer in glacier science, who is currently Professor Emeritus in Physics at the University of Bristol. John Nye's paradigm-changing work in ice rheology theory allowed us to predict glacier behavior, including surging glaciers, as land ice responds to climate warming. Nye's work in ice mechanics and glacier bed dynamics is as relevant today as it was when he first developed his theories 50 years ago. Like John Nye, Liz Morris is a leader in glaciology, Her unique blend of rigorous theoretical modeling and careful fieldwork has led to seminal advances in snow hydrology, glaciology, avalanche studies, and field measurement techniques. Her interests and publications span many different aspects of snow, glaciers, and ice sheets, modeling of mass and energy transfer, dynamics, remote sensing, hydrology, variability and climate change. She was one of the first British women to visit Antarctica and has carried out 6 expeditions in the Antarctic and 13 in the Arctic, truly a bipolar cryospherian. She's served the cryosphere community as president of the International Commission on Snow and Ice, ICSI, from 1995 to 2001, and president of the International Glaciological Society from 2002 to 2005. She was honored for her services to polar science with an Order of the British Empire in the Millennium Honors List and a Polar Medal in 2003. Her breadth of accomplishments and important contributions identify her as a true cryospherian, and we're proud to have her as our Nye lecturer today. Please welcome Dr. Liz Morris. Thank you. Okay.
Right,
And forward.
okay. Well, thank you very much, Anne. First, I think I should probably do a volume check to make sure that everything is working okay. So wave your hands desperately if this is not working. Okay, good. Well, that's a relief. I have to say it is obviously a very great honour to be asked to give the Nye lecture, not only because this comes from the cryospheric group of the AGU, the very distinguished cryospheric group, but also, of course, since it's a particular pleasure for me, since I was, in fact, a student of John Nye many, many years ago in Bristol. And the training that John Nye gave me then has stood me in very good stead throughout my career as a scientist, and has led me really to very much what I think is the heaven for glaciologists, which is depicted in the picture there, trudging peacefully across the ice sheet in a storm, going to change your batteries with not a care in the world. And without John, I would not be able to do what I'm doing today. So I have a lot to thank John for. Well, I'm going to start off by telling you a bit about what I'm doing at the moment and why I'm going to be talking about the things that I'm going to talk in this lecture. Basically, this week, we're all of us going to be concentrating on the details of our particular field of expertise in glaciology. We concentrate on the outer limits of our subject, the very new and the very difficult. And although at the AGU we have the opportunity to move around and look at different fields, it's very difficult to do that. It all seems a bit overwhelming, at least to me, that the press of keeping up with your own subject is quite hard enough without going to listen to other things. So really, the Nye lecture is the only opportunity where we all have to come together as a group, as glaciologists over a very broad span of interest, and just think about a topic together. And I'd like, therefore, to talk about something which I think will cover the interests of a lot of people here. And basically, it's the problem of going from what we know about a substance in detail, looking at it in the field or in the laboratory, and how we put that into some sort of system, some kind of model, in order to be able to solve problems which are of some use in the world and make us of some use in the world. So turning to what I'm doing at the moment, I'm working on a project to provide ground truth for the Cryosat satellite, which at this very moment, I hope, is flying above us, and was launched by the European Space Agency a couple of years ago. Now, there was really, quite unusually, I think, a very tight plan made for how we should validate and look for errors in the Cryosat data. And the 3 pathways were defined for measurements over the land ice, with similar sorts of pathways for the sea ice component. First of all, you have to find out whether the instrument is actually working properly. And this is a radar altimeter, so we're looking at problems of retrieving the surface from the radar signal. Secondly, if you have a measurement of elevation and you want, in the end, to know something about the mass balance of ice sheets, you do have to find a way of going from elevation to mass, and for that you need to know quite a lot about the spatial variability of density. And then thirdly, of course, if there are changes in mass in the ice sheet, in surface mass balance, are these significant? Are these a long-term trend? Or are they just part of the normal fluctuations, if you like, the year-to-year fluctuations of accumulation? Now, the last two pathways are obviously things which apply to any kind of altimeter measurements, but the first of these was the one which was particularly of concern to ESA, and which led to them funding a whole series of ground truth experiments, in fact, over the last 11 years. In fact, it was very fortunate for us ground workers that the first satellite blew up on launch, because it meant that our validation program was greatly elongated. And so we've got really a very nice collection of data, thanks to the Ukrainians who programmed the rocket which blew up. I have to say that we have been working very happily with our American ice bridge colleagues who dealt with the problems of satellite malfunction or not quite doing what you want in a different way by turning an aircraft into a satellite and doggedly flying it everywhere. And I'm not quite sure whether Michael Studinger and his team have done more miles than Cryosat has, but they've certainly tried. So our plan was to use airborne measurements to allow us to jump between the point measurements on the ground and the satellite measurements to do the upscaling, help us with that. So on the ground we had radars which were quite similar to the satellite radar, and then we overflew the ground sites with aircraft carrying similar radars, and then finally we could compare the signals we were getting from these radars with the one that the satellite was getting. Unfortunately, the radar's not exactly the same, but pretty close. Our task, as far as ESA was concerned, was really to look at the radar returns and see whether the effect of going upwards from the point up to the satellite was changing the radar returns, just to see whether the elevation was right, whether if you measured the surface elevation of the snow surface, you actually were getting the same elevation from the satellite. And the answer to that one, of course, is well to within plus or minus 5 meters or so. So, this fair amount of correction has to be done. We needed to measure surface roughness so we could see what the effect on the signal was of surface scattering, and similarly look at the snow stratigraphy so we could look at volume scattering. And finally, we were really interested in trying to make repeat measurements at the same time, repeat measurements at the same place, because we want to look at errors in elevation change, not in elevation itself. All of that led to a quite massive program of overflights using 3 different aircraft. The German Dornier aircraft carrying a thing called the EM Bird to look at sea ice, a Danish Twin Otter carrying a radar, and our friends the Americans in their P2. And also quite a logistics operation to get everybody into the field at the right place at the right time. Well, my part in this sort of rather large international program was to travel back and forth year after year along this traverse, which goes from a place called T5 on the old Agig line on Greenland, up to a place called T41, and then hang a left up to Summit Station. These were our primary sites, and the rest of the UK team was working on sea ice in the Arctic. You can hear a lot more about this, of course, in the Cryosat session, which comes on Friday. So it really is worth changing your tickets and not flying home before this key session, which comes on Friday afternoon. Our task, of course, first was to make sure that the aircraft actually flew over us, and we therefore surveyed in radar reflectors, and the aircraft's task was to hit that radar reflector, get that in the signal, and then see whether its idea of where the ground one was the same as ours. I have to say, in my first season, I disgraced myself by sitting patiently by the radar reflector on a sledge covered with aluminium Zargis boxes, waiting for the overflight to happen. And there were a few tantrums from the radar people when they found a really rather large number of reflectors in their signal. But we got that one sorted out. Making measurements over a nested grid at different spacings allowed us to look at the spatial variability or the snow properties. And we tried to record what the surface was like. But this, I think, was the thing which was most difficult for us to do. All sorts of different surfaces, from blowing snow to sastrugi to a very wonderful, sort of very light hoarfrost surface in the summit part of Greenland, where you can see my companion is sort of up to his fetlocks in the stuff. It's very, very smooth. And then, of course, the sea ice with all the humps and bumps that you get there. And I don't think we ever really found a good way of characterising the surface in a way that would be helpful. But we did a lot better with the snow stratigraphy. And we could pick up in detail the layers of hoar in the dry snow zone. That's the well-known couplet of winter snow and summer snow in the polar regions, or the ice melt layers in the percolation zone. And finally, I ended up with a really rather nice trove of data on spatial variability in snow density, which was what I was being asked to find by the Cryosat project. And then really quite coincidentally, a whole series of data on the variation in compaction rate at the same site over time. And this set me thinking about what it was that was controlling densification in that area. And I started to worry about densification, and indeed started to try and put together an equation for a new compaction law, and I'm going to be talking about that in this famous Friday afternoon session as well. So I won't go into details, but merely to say that I got to the point where I had a nice field-based equation, and I thought, well, that's it then, that's fine. I'll just bung that into a model. How about SN therm or something like that? And away we go with a new equation in the model. And then the voice of conscience really spoke. And I like to think that, having once been in the same laboratory as John Nye, I couldn't really commit that crime without something in me saying, hang on a bit. And I thought, no, you better go away and think about it. And that led me to do some reading and some thinking about what's going on now, and really leads to the real subject of this talk. Now, I want to talk to you about mixture models, and that, well, to be absolutely formal and polite, I suppose I should say continuum mechanics, the continuum mechanics of mixtures. But there is a bit of psychological barrier in that this stuff often arrives in a trailing clouds of equations and generally produces a fair amount of a gulp in those of us who don't really feed on equations most of the time. But I think it's worth trying to have a gentle historical sort of canter through this, just so that I can make some points in the end about what we do about dealing with things like snow, and indeed the other subject of my talk, which is hot ice. I've gone back now, and the baby from Giles, if you're British, you'll recognise the baby, is the baby scientist who was in John Nye's lab. And I have to say things were not going well at all. John Nye, of course, was a very great theoretician, but he did do a few experiments, and one of these was the very elegant bubble raft, a very, very light and fragile experiment which told you about dislocations. So he was a bit bemused, I have to say, by my model glacier, which was made out of 2-inch sheet steel and required a crane to lift it into the fridge. And what was worse, my model glacier was not working and was not producing regelation as I'd hoped. So he did what all good supervisors did, which was divert my attention and set me to looking at veins and inclusions in ice which he was looking at with Shinji Mei, his postdoc then. And here you can see the thing which will be quite familiar to people who've looked at warm ice, and that's the fact that water is contained in the grains, between the grains, in veins at the 3-grain intersections, and also in inclusions at 4-grain points. And you also, of course, have bubbles, all sorts of things going on in ice. Well, I moved on from John to actually work as a hydrologist on the very first physics-based hydrological models. And this is actually a sketch of something called SHE, the Système Hydrologique Européen, but all of them were much along the same lines in those years. That's to say, you tried to represent the physical processes going on in a catchment by equations and solved them on a grid, and some of the processes you regarded as one-dimensional. So, for example, snowmelt is there as a one-dimensional flow vertically, and others you solved two-dimensionally. And that sort of approach has been taken forward now in various models. SN Therm was written by Rachel Jordan in 1989 and updated and really gone over very thoroughly by Mel Sandals to form SNOWCAN 10 years later, I think. Crocus came at about the same time as SN Therm. That's Eric Brun and his colleagues at Meteo France. Daisy was written at Davos and has been now superseded by Snowpack, which is perhaps the latest of all these models. And all these models are mature in the sense that they've been used in very many different circumstances, and they're also quite available to people. In fact, SN Therm, I think, is open source, so that there's a temptation for everybody to have these models on their computer, and it's very easy to code something in and say, well, all right, I'll just change this line. And since you didn't write the model, not be quite aware of what the consequences are. At that time, I didn't really know what I was doing. I was just saying, well, let's treat snow as soil. But I soon found a paper which treated everything far more rigorously, which was a paper which introduced me to the idea of mixture theory. And I think the person who was behind all of this was in fact Bob Besant, who is still at the University of Saskatoon. And he introduced me to the formal definition, if you like, of the mixture, which was of something where the distance between the particles was so small compared to the dimensions of the differential volume that you were going to use, that you could regard it as a continuum. Now, snow obviously isn't the only thing that you could treat like this. You could think about till, and people do think about till as a continuum, model the flow of till, even though you know that there are things inside the till of different size. And you might want to say something about, for example, the elongation of particles in the till. You might want to say that all long particles have their long axis in the direction of flow. But that still doesn't stop you treating the material as a continuum and saying, I don't want to specify exactly where all these particles are. Similarly with sea ice, you don't want to say where every pan of sea ice is. You just want to say something about a continuum, which is a sea ice mixture, if you like, of a certain density. And you can see that it would be easy to say, well, the albedo is going to be a straight mixture, the area of white plus the area of black gives you the albedo. But it might be a lot more difficult to formulate laws which were suitable for turbulent transfers, for example, or indeed for the dynamics of the sea ice. And I was talking to Danny Feltham, who reminded me that, in fact, John Nye actually did make a very big contribution to sea ice modelling in his early work in the AGEX project, which was dealing precisely with the sort of laws that you needed for sea ice to treat it as a continuum mechanics problem. You can go to the very small. You can look at polycrystalline ice and think, well, all right, that's a mixture of ice grains with their c-axes pointing in different directions. Or you could go right to the other end of the scale, because there's no scale limit on doing this, and do what Gary Clark and Sean Marshall did, which I think is really entertaining, which is treat ice sheets as a mixture of stream ice and sheet ice. Well, okay, so I applied mixture theory in the ski snow component, and then had the great privilege to apply it to Britain's premier ski resort, which is Cairngorm Mountain. I have to say that other people seem to have rather nicer field sites than I did. At the same time, Jeff Dozier and his friends in California were basking in non-stop solar radiation, and they were modelling it as well, very well, but even so, it really wasn't fair. And it has continued. Every time you send a student off to Idaho, for example, I think, well, you know, in the old days we had to suffer. Well, this picture is really here to remind me to say to all the modellers here that I know that, you know, the business of scaling up is actually very, very complex indeed. And you could very well argue that fussing about the equations that you're going to use for what actually happens in the snowpack is pretty damned irrelevant if you're faced with a situation like this. However, I'm going to put the opposite point of view and say that it doesn't hurt to do things properly. If you actually do the continuum mechanics of a problem, and then you find that you have to knock out dozens of terms, well, you haven't really lost anything because you've learned why you're knocking out those terms. Whereas if you start from a simplified model, you don't actually know whether you've lost something or whether you might have to add something if you go elsewhere. So the real question is then that was struck me was, well, what really are the right equations to use? And I was very, very fortunate at that stage of starting to work with Leslie Morland, who was one of the towering guys in continuum mechanics at the time. And it was really serendipity. I happened to have worked with Leslie on completely different things. We knew we got on well together, so we could set up a partnership and just attack this problem. And Leslie, of course, was well linked into Collie Hutter, who was another of the great figures. And the person we didn't really know was Bob Brown, but the American avalanche community were going along the same path at the same time. Right, okay, close your eyes, or alternatively, look at the simultaneous translation in the boxes. But I just really want to introduce some equations. As you might expect, it all begins with the conservation laws. You have to have conservation of mass, and the idea is that you can write a conservation of mass equation for the mixture as a whole, or you can partition up the components and write equations for each element of the mixture. Now, if you're only interested in whether you've actually got any ice cream in the box, you don't have to open the box, you can just weigh it, and that weight will stay the same, whatever the temperature in the kitchen. If you want to know whether the ice cream is fit to eat, you want to know something about the proportion of ice to slop, in which case you really want to do something about the components. This is a bit of carefully placed product placement, by the way. I'm hoping that you will realise that this is the stuff to buy and that the Scottish ice cream industry will be in for a boom, and a grateful country will give me a sort of a week skiing in Cairngorm to thank me. Anyway, there's the mass balance equation, and in it, the things you have to notice are in red. In it, there's the mass transfer, which is an interaction term. And the point is that these interaction terms all add up to zero. In other words, what you gain by more freezing, you've lost from somewhere else by the fact that you've lost some water vapour or you've lost some water. And the volume fractions are, of course, they all add up to 1, not to 0. Sorry about that. Volume fractions all add up to 1. And the general idea of this very simple theory that we were setting up at that stage was that you partitioned everything according to these volume fractions. So not only the densities, but you also partitioned things like pressure and any other quality of the mixture that you were going to talk about. If you write down the momentum balance, you start seeing various terms in red. You really do not have to bother about this equation if it doesn't, if it's not absolutely familiar. But just look at the red bits and see that if you write down the equation for the mixture as a whole, it's got a red bit in it. And that's merely saying that if you want to transfer mass by melting or refreezing or whatever, and you want to have different velocities for the different phases in the mixture, you've actually got to move that mass to its new velocity. So there's a momentum effect coming in for the mixture. Now, I was hoping to have a picture of me whirling the ice cream round my head on a string, which I thought would probably do the momentum bit for you, but that was vetoed on the grounds of health and safety in my household. So you just have to picture that you would know that whether the mixture was melting or not from the tension on the string. And for each component, we have, again, interaction drags. And those interaction drags are, in fact, what's happening when one of the elements passes through the other. So in the case of snow, let's say when water is flowing through the ice matrix. Okay, now in the classic theory, you go through the maths, you work out some kind of idea about what you think the interaction drag should be, and lo and behold, this all ends up as Darcy's law. But on the way to Darcy's law, you're knocking out terms, and you know why you're knocking out them. They may be negligible in this circumstance, but they're not necessarily negligible in all circumstances. Okay, well, as a break from that, I'll tell you a bit about Nico Gray's rather nice avalanche experiment. Nico's got a rotating drum. And if you can imagine, this, we're looking at it sideways on, and it's filled with a mixture of red, green and white spherical balls, which are of different sizes. And the mixture is coming up, the drum is turning round in clockwise direction, the mixture is coming up to the top left-hand corner, and then it's falling down the surface in an avalanche. And it's sorting itself, so that by the time you get to the bottom, what you're shedding into the bottom is a sorted mixture of the small red grains, the medium-sized white ones, and then at the top, the big green ones. Looking at that in a little bit more detail, you can see this is a snapshot of the very centre. So you can see the stuff coming in, the source is mixed with the different particles, and then the avalanche is gradually separating them out and shedding in the small bits at the bottom. Well, the only way that Nico could find to model what was happening in that mixture, because it is a mixture, was to make what he regards as a pretty bold assumption. It seems fairly reasonable to me, that the particles are not actually sharing the overburden pressure, supporting the weight of the ones above them equally, but according to size. So in other words, the big ones are actually holding up everything, and then the smaller ones are just falling through quite freely, and that's why you've got the sorting effect. And this I've put in really as an example of the fact that you don't have to follow the rules of Leslie's very classical mixture theory. You can make different postulates about how you're going to sort out what the various fractions do. But if you do that, there are consequences throughout the rest of the theory, so you have to follow it through in everything. So if you want to have different pressures carried by each fraction, not just according to their volume fraction, you've got to go along the line which Nico has actually outlined in his paper. Finally, there's an energy balance equation, and that's so complicated to write down for the mixture, you might as well just write down one for the component to see what it is and to show you that it's got interaction terms in it again, which are all about the interchange of latent heat, not only directly but also knock-on effects. Okay, and I've actually written that in terms of internal energy, which is actually quite a good thing to work in terms of, rather than going into, let us say, something like temperature. And I noticed that there's a really quite nice poster on using enthalpy, or in this case internal energy, rather than temperature as a variable in the poster session. Well, finally, Leslie got to the stage where he wanted to complete his model with what's called constitutive laws, which is laws about the particular substance that you're modelling. And this is where the physicist comes in, and it's very much the sort of washing up operation for your mathematician. You know, he has a wonderful time in the kitchen throwing the ingredients around, and you come along to sort of sort out the boring stuff. Well, the boring stuff is actually really, really difficult, and there are two ways to do it. You can look at things on the macro scale, and this is probably what your mathematician wants you to do. He wants you to say, at the mixture scale, so when you've got lots and lots and lots of stuff, can you do me an experiment which shows how the volume fractions are actually related to bulk parameters like temperature or pressure? Well, this is a mixture scale experiment, or two of them, in fact, by Sam Kolbeck and Tony Vankiewicz, long time ago, looking at the water content of wet snow and how it changes with the applied pressure, in this case, an applied tension. And you can see that, you know, we've got all of three curves, which is good. Unfortunately, they tell us that summer snow, the red stuff, and winter snow hold different amounts of water. And Sam Kolbeck's one is particularly worrying because it looks as if it goes on forever, which is a nasty thing to have in a mathematical model, that there's an irreducible water content, whatever you do to the wet snow. The other way to do it would be to say, well, all right, I'm going to make some kind of assumption and then try and work this out from the grain size distribution in the snow, from the detailed microstructure of the snow. And that's one of the things I tried to do, using Sam Kolbeck's geometry for the equilibrium state of water in snow, you know, with these little rings of water around the snow grains. And, you know, with a bit of a struggle, you can work out what the curve should look like. And it does look a bit like the macroscale curves, but is clearly not right at the two ends of the curve. Well, coming back to the problem which is worrying me at the moment, which is one of a constitutive law for snow, a compaction law for snow, people have been at this on the microscale for some time. One of the interesting things is that if you go back and you read your all-time great star papers, and I have to say Richard Alley's paper on grain boundary sliding is one of my favourites, but you tend to forget some of the things that Richard has said in the paper and glide over them because you're so busy thinking about the equation he comes out with in the end. One of the things he says, of course, is this does not apply where there's a temperature gradient. It deliberately says that temperature gradients, no. And the other thing he says is that the pressure is partitioned so that the ice grain matrix is carrying pretty well all of the overburden. So there immediately you've got something which is actually a bit like Nico's situation and is not like the situation which Leslie Morland, for example, and I were using in our models. Perfectly fine to do it, but you've got to realise it's being done and then make sure that the rest of the model actually keys in with that if you want to use that equation. Well, talking a little bit now about temperate ice, Heidi Mader at Bristol was carrying on John Nye's work on the water veins in glaciers, and quite a lot is known now about the microstructure of water content around grains. The problem is that this is pretty difficult to apply actually on the large scale in modelling a glacier. The water is there quite often because of impurities. It's located at the edges of grains, but these grains may recrystallize as the glacier ice moves, and therefore the water vein network is moving through the ice, gathering water from some places and shedding it into others. So it's not quite a simple static system. People tend, as far as I can see, to use a macroscale equation, which ultimately derives from experiments which were done by Paul Duval to show that he had a viscometer which was about 10 centimetres in diameter and 1 centimetre wide. He deformed that ice, and he found that the strain rate for the ice for a constant applied shear stress actually got greater with the amount of water held in the ice. That's a sort of quite convenient law to use, but it's arguable that it might now be the moment to start thinking about mixtures of water in temperate ice in a slightly more sophisticated fashion, because this, after all, is a very small-scale experiment to be using for something which is essentially quite a large-scale thing going on. Well, now I'm speeding up and coming up to present day. Over the years, some very successful modelling has been done, basically using continuum mechanics for temperate ice, of a mixture of ice and water. The star names are Collie Hutter and Andrew Fowler, and their work really has shown how water content affects ice viscosity, that affects the strain rate, that affects strain heating, which can also, going back to affect the water content. I looked to see what was going on at this very moment, as it were, as we speak, and found this very nice paper by Andy Ashwanden, which is a map, if you like, a model of the Greenland ice sheet, which shows the areas at the base of the ice sheet which are warm and the areas which are cold. And this was used using the parallel ice sheet model, which very much takes this approach. Okay, on the snow front, snowpack has gone from strength to strength and is continually being developed. And the latest, most interesting paper that I found was a simulation of the snow cover in the snow site below the Davos Institute, and that's another rather nice place to be getting data from, showing that in fact you don't have to make the usual postulate that people do, which is the temperature of the ice and the temperature of the gas in a dry snowpack is the same. This shows temperature differences, and you can see that there can be quite substantial temperature differences in the snowpack over the season. Crocus is also being developed and still operational. Crocus has been linked to MET models and to land ice models, so that there's land models, so that there's a possibility now of looking on quite large scale and modelling things, for example, like blowing snow on this site, the Col de Lac Blanc, I think, and basically looking in detail at the effects of winds which you put its input into the model. So these models, as I said to start off with, are mature and are available really as structures, as computer containers, if you like, to put in different equations if necessary. So I think the problem is not at all in how to solve equations or the general structure of putting data in and putting data out. What we really want to do is to see where we are now in the case of looking at the equations which should go into the models. There are new observation methods, and this is a shameless advertisement for my ex-student who's got a poster tomorrow. Adrian, in the true tradition of the Nye bubble raft and the Liz Morris 2-inch thick glacier, he went one better and put this cone penetrometer testing kit on the back of a tractor and went to the Antarctic and looked at the strength of snow. And you can see it's a pretty hefty piece of kit, and rather nicely we can see that the strength of snow is pretty well linked into density, therefore but also we've got the opportunity of getting something a bit more also about the microstructure of the snow. My neutron probe gives us the opportunity to get two density profiles from the same site at different times and use those to look at strain rate. The strain rate curve, which is the lower one, you can see that there is an effect of density because the strain rate changes as you go down through the snowpack, but there's also a distinct fluctuation with something else going on. And we're beginning to pin down the fact that densification depends not only on the bulk parameter, so the volume fraction of ice, if you like, but also on something else in the snow, which at the moment I'm just calling the type of snow, but can be to do with grain size, coordination, and so on. Again, an advertisement for our session on Friday. I think the most interesting thing, though, is the use of microtomography, X-ray microtomography. And this is fantastic because it gives you the chance to look at snow in detail and in vivo, as the Swiss put it, actually as it changes. And here you can actually see what happens to the same piece of snow when it's subjected to -3 degrees centigrade over a year. This opens up all sorts of possibilities because you can actually use pretty sophisticated analysis techniques to look at the statistics of how those grains are distributed. So you've got something more than just volume fraction to play with. And the real challenge is how to use this new knowledge that we're getting about the microstructure of snow to make new laws to go into the models. Now, Henning Loh very, very kindly gave me a sneak preview of some of the things he's going to talk about. This is just one example of the work that the younger scientists are doing now, and which is really, really exciting. Henning has taken real snow, the structure known from the tomography, and calculated the vertical component of thermal conductivity for that real sample of snow. He's then also calculated what the ice volume fraction is for the real sample. If you plot one against the other, you can see that these various samples are scattered around a curve, which might be the sort of curve which was a first approximation about how thermal conductivity varies with ice volume fraction. Now, recall that in the theory that we set up originally, everything was just partitioned according to ice volume fraction. So that thermal conductivity should just go with as linearly with the ice volume fraction. It doesn't. There's something else going on. And the nice thing is that Henning has been able to specify a parameter which describes what else is going on, which is to do with the coordination number, the distribution of grains. Well, that's it. The question really was three-phase mixtures or something more. Well, if you're talking about a classic three-phase mixture in which everything is distributed just according to volume fraction, the answer is ice, wet ice and snow certainly aren't like that. If you're prepared to be a little less rigid about how you describe a mixture, then certainly yes. The continuum mechanics approach continues to be the best way to go. We've got whole new things coming up which are moving what we need from the mixture theory in different directions. We certainly need to take account of the statistics of the distribution, and I know that as far as the ice sheet modelers are concerned, they're well away with new theories which talk about isocrystals as a mixture of different size and orientation. The last point I'd like to make is that I've had a wonderful time talking to mathematicians about this sort of thing. All of them have been quite nice. Even the ones I don't know, if you look at their pictures, they look quite nice people to meet. So I would like to urge everybody who's going to dip their toes into this to find yourself a nice mathematician to work with, because that way you, as well as I did, will be able to get it right. Thank you very much.
Thank you very much. And we have time for questions, and I'll let Dr. Morris field the questions, please.
Oh, my goodness.
If you can see, but I'll see if I can help.
Yeah.
It's hard to see.
No. I think on to the celebrations.
Well, okay. All right. Well, I'd like to make one more announcement then. The Cryosphere Reception this year is starting at 6:30, and this year it's at Hotel Intercontinental on the 3rd floor in ballrooms B and C, and it starts at 6:30. And it is a ticketed reception. They will be selling some tickets. If you don't have one, please join us. And tickets for students are only $8. and tickets for regular members are $13. And we look forward to seeing you there. And please, let's thank our speaker one last time.